Hello everyone, I am Pollatta Serialage Satin Chamikara. Today I am presenting a predictive analysis of bike rental demand using the AWGWAFIT 718 framework. We will explore how advanced aggregation functions can be leveraged to solve complex urban mobility challenges for the next generation of smart cities. Our startup team has developed the AWGWAFIT 718 framework in R to help urban mobility centers predict bike demand. By accurately forecasting usage, operators can optimize fleet distribution, ensuring bikes are where they are needed most, thereby increasing investment potential and operational efficiency. I selected the bike sharing dataset from the UCI machine learning repository. It contained over 17,000 samples and 17 attributes, providing the necessary complexity for aggregation modeling while easily meeting our assignment's minimum criteria. To ensure the model is robust and generalizable, I split the data into two groups. Set A consists of 1500 samples used for the iterative training and model fitting progress, while set B contains 500 samples reserved for final testing on unseen data. Our strategy focused on business relevance and statistical integrity. Critically, I removed the casual and registered variables. Since their sum equals the target count exactly, including them would cause the target leakage, resulting in an artificially perfect but useless model. I finalized 10 high impact predictors. These include environmental factors like temperature and weather severity, alongside temporal factors like the hour of the day and working day status. These variables collectively capture the behavioral drivers of the bike demand. Our histograms reveal that the target rental count is heavily right skewed, meaning peak demand hours are rare. While temperature shows a normal spread, the hour variable is multimodal, clearly reflecting the high usage during morning and evening commutes. Scatter plots confirm a positive trend. As temperature rises, demand generally increases. The hour versus count plot shows the distinct M shape, highlighting that the primary business opportunity lies within the 8 am and 5 pm rush hour windows. I applied non-linear transformations to stabilize variance and align the features with the target behavior. This included squaring the temperature to capture accelerating demand and using logarithmic transforms for humidity. Finally, all variables were mean, max, normalized to a 0 to 1 scale for fair aggregation. We evaluated three main types of aggregation: the weighted arithmetic mean, the ordered weighted average, and multiple variations of the weighted power mean. This allows us to find the specific mathematical curve that best fits the non-linear nature of the bike rentals. Comparing to our results, the weighted power mean was the clear winner. It achieved the lowest RMSE of 0.1762 and the highest Pearson correlation, significantly outperforming the standard arithmetic models. The success of the model makes sense from the common sense perspective. Bike demand doesn't grow in straight line. It has sharp peaks and non-linear bursts. This specific power mean is mathematically better at capturing those nonlinear interactions than the standard average. Our model identifies a temp or perceived temperature and hour as the most critical factors. Interestingly, variables like season and month received zero weight. This suggests that the model is smart enough to realize that if we know the hour and how warm it feels, the calendar month becomes redundant information. When testing on the unseen set B data, the model maintained a correlation of 0.5299. This is very reasonable and consistent result for real-world environmental data, proving our framework is reliable for future forecasting. While the model is powerful for preemptive fleet management, it has limitations. It cannot account for black zone events like sudden transit strikes or extreme storms. Businesses must combine these model outputs with real time weather alerts for maximum reliability. We prioritize ethics by using anonymized data with no personal identifiers. However, we must also consider algorithmic bias. If we only place high demand areas, we may unintentionally neglect lower income neighborhoods, which is critical social equity consideration. In conclusion, AGGWAFIT 718 framework successfully identified the primary drivers of bike demand. It offers scalable, data-driven foundation for smart transport logistics that is ready for investment and deployment. Thank you. Finally, here are the references for our data sources and the R packages used throughout this analysis, including the UCI repository and the IPSLOW library. I am now happy to take any questions.